The Bachelor of Science with top honors from Cairo University and a master's and a PhD degree from Stanford University.
Did I?
Dr. Solomon, I believe maybe she get disconnected, but you can
Yeah.
start and I will
I
leave
have
the part in the editing.
Okay, very good. Okay. Thank you everyone for attending. Thank you, Mariam, for the introduction. Thank you, Ahmed, for arranging this teaching, giving me more work to do than as if I don't need any more work. Anyway, this is the second lecture. We talked last week about history of hydraulic fracturing. I should have also mentioned last week that Mr. Buddy McDaniel is an old friend of mine and a colleague that we did a lot of work together, was the biggest contributor to the writing on fracturing, history of fracturing, fracturing was both vertical and horizontal. So when you read this presentation, please remember that I should have acknowledged him as a very knowledgeable person that we did a lot of work together. Last week, I also talked about fluid flow, and I mentioned the pseudo-radial flow and elliptical flow. So what I did, I'm having another 4 slides here to show you some numerical simulation of how the fluid flow would look. Just a simple case where I have a vertical hydraulic fracture in a formation and make it penetrating the whole formation to show you how the fluid flow would look. I'm showing a couple of illustrations. There will be 2 slides on infinite conductivity fractures and 2 slides on finite conductivity fractures. So here I'm saying CFD, and if you remember the definition of CFD, which is permeability of the fracture times the width of the fracture divided by formation permeability, and also divided by fracture half length, one wing of the fracture. And here I have very tight gas formation. So it takes, the conductivity basically infinite meaning that the pressure drop inside the fracture is negligible relative to the pressure drop inside the formation. And you can see here the behavior looks very much as if I have just a line inside the formation. That's what will give me linear flow. After a long time, you can see the pressure drop around the formation is demonstrated here. If I look at the outer boundary where the pressure has been significantly affected, the rest to the red one here, the red area, basically saying we have not affected this area at all. So nothing coming out of, or very, very little coming out of this red area. Most of the fluid is coming out from this affected area. And you look at the affected area, it's elliptical shape, but it looks almost like a circle. So it is almost radial flow, and this is the reason you call it pseudo-radial flow. If I have finite conductivity fracture, you can see the effect is not as strong, and you don't see the end of the fractures right away. So it takes some time to see the end of the fracture. That is the bilinear flow. If you remember, we talked about that a little bit. And you can see with time, you end up seeing further and further into the formation, but the elliptical behavior is more dominant here till eventually you reach the pseudo-radial flow. Pseudo-radial flow, which is almost radial flow. It is still kind of elliptical. However, the major and minor axes of the ellipse are almost equal. If they are almost equal, so they are almost having radial flow. So that's the reason you would call it pseudo radial flow. Fracturing, part of it is fluid flow. So we discussed that. Today we want to talk a little bit about rock mechanics and in situ stresses. Next week we'll talk about fracture mechanics, and last week we'll talk about testing. And please remember, that that this is very introductory. We don't go in things in a huge details. We teach a graduate class I taught it in Texas Tech, and we'll teach it here at UH, where we go into all those areas in a lot more details and theory. So it is over 16-week, 3 hours per week, and homework and midterms and all kind of things. So let us talk a little bit about rock mechanics, because that's what we need to understand just before we get into stresses. So what is rock mechanics? Basically, it is a discipline that you use to describe the behavior of underground formation and rock under in situ stresses, or sometimes externally applied loading conditions. That's what you do in hydraulic fracturing. And when you couple the fluid and the rock mechanics together, that's when you talk about geomechanics. And we'll be talking about both in the rest of the hour. Is it important to study rock mechanics and geomechanics in petroleum industry? Absolutely. Unfortunately, it has been ignored for a long time in teaching undergraduate and graduate classes, and that's a mistake, because it's important in drilling, borehole stability, what happened as you drill. We'll mention a few little things as we talk here. Formation breakdown, if your downhole pressure or the wellbore pressure, if it's too high, you could fracture the formation. If it is too low, you could collapse the wellbore. So it's very important to understand all this relationship in rock mechanics and the fluid flow. Stimulation obviously is very important. Fracture initiation pressure, we are going to look at one equation here. We spend a little bit of time on it for fracture initiation pressure, because it's very important to understand. Then next week we'll talk more about the fracture propagation pressure. To initiate the fracture requires certain pressure. It's going to be a little high pressure. People observe that once you fracture the formation, then your propagation will be at a lower pressure, but you can pressure that can be increasing with time, and one has to be able to analyze that for propagation pressure. So we'll be talking about that both next week as well as in the testing part. And then all of that related to fracture geometry and designing of a fracture. That's all important. Then you get into production, and then there is a lot of aspects in rock mechanics, failure of the formation, sanding. We're not going to get into sanding at all in this course, because it's more hydraulic fracturing. But sanding is very important, and in a graduate class we end talking about sanding, the onset of sanding, and the calculation of how much sand you produce. You want to talk about some of the assumptions we work with. We can say, well, formation, many times, especially when you study well testing, they tell you homogeneous, the formation is homogeneous and isotropic. There are two different things. Homogeneous formation means that if you take one element in the formation, it's basically represented the whole body as the whole formation. That's a little different for being. So many of the formation we look at, many of the assumptions we make is the formation is homogeneous. Really, if you look at the formation at a very small element, they are really not homogeneous, but it is distributed so much that many of the formation they behave as if they are homogeneous formation. So we'll look at some of this. Hopefully, we can spend more time on it because some of heterogeneities can be very important. When you get into heterogeneous formation, such as dual porosity shale, carbonate formation, this have a very strong effect on fracture propagation. We deal with it a lot in our work, especially when you get into shale formation and when you analyze data. Isotropy, whether you call formation isotropic or anisotropic, that means a dependence on direction. So a formation may be isotropic and homogeneous, and maybe anisotropic and homogeneous. So if I have a formation that is, say, permeability in one direction is different from the other, so it can be homogeneous, but it's still anisotropic. Isotropic would mean that properties in various directions are the same. Now, when you talk about rock mechanics, many times we make the assumption that the formation is linearly elastic. Basically, linearly elastic is as if you're looking at a spring. So you push the spring down, you compress it, you relax, it goes back to original shape. So, and we'll describe it a little bit more detail mathematically in a minute. But basically, all we're saying here is the formation will disappear once you remove the external forces. So how realistic they are? Essentially, I talked about that. Homogeneity many times is good assumption unless you get into a dual porosity or natural fracture formation, or it becomes important. We are going to see that the importance of heterogeneities when you talk about fracture design, and especially when you talk about analysis. When I get into analysis, I will show you something that we have been doing, and especially for shale formation, that heterogeneities have to be considered. The presence of natural fractures will have to be considered, which makes the formation heterogeneous. Isotropy, usually in a horizontal plane, it properties may not vary very much, but we many times we assume isotropy, but you are going to see in testing again, and even in design, it can have an effect. Linearly elastic material, if we have hard rock, and we'll talk more definition of what hard rock is. If we have hard rock like sandstone, then the behavior would look very much like linearly elastic. But if you get a soft rock, such as when we fracture in Gulf of Mexico, and I'm sure in areas where you live and you work. So in Gulf of Mexico, they are soft rock, so the behavior is different. It cannot be exactly considered linearly elastic. So there is other ways to handle that behavior. So if I look at it, when I say, and will be more of this in a minute, when I say linearly elastic, if I plot stress versus strain, and we'll talk about this in more in a few minutes. If I increase stress, I get more strain. So basically, it is like if I have a core and I compress it, very much as if I'm compressing. You look here on the left-hand side, as if I'm compressing a spring. So if I compress it, it gets shorter, and then I release it, goes back to original value. And if you look at here, stress versus strain, so it's going in a straight line. If I release it, goes back on that straight line. So not only this is linearly elastic, but there is no hysteresis. So it goes back on the same line. Does it always work this way? No. But this is a simplification that many people use. In reality, it may look like the curve we have here beside it, and that early part of behavior, which is an elastic strain, we used in some special testing. Unfortunately, I'm not going to get into that even in the testing part. It's too specialized. But we have used it many times. I mean, when we get to testing, we may be able to say a word or two about it. Eventually, in any of those curves, if you've studied material science, they will tell you, after some time, if your stress gets too high, the formation may fail. So you can have failure of the formation. That's a plastic behavior, so it cannot be reversed. Poor elasticity is very important concept to understand, where it affects the fracture, affects the rock behavior, and we'll talk more about it in a few minutes. For example, here, we're having two straight lines showing whether it is drained, same like the one above, stress versus strain. I probably should have defined what stress is. Stress is, have the units like pressure, is PSI, force per unit area. However, it is not the same as pressure. Pressure usually is used to describe fluids. So pressure is a scalar quantity. Stress is a vectorial quantity, meaning that it has orientation. We'll see that in a minute. So here I'm saying whether the rock does not have any fluid in it, it will follow different curve or different line than if it has fluid on it. And then we'll talk about stiffness versus frequency. We'll get into that in a little bit, because we can sometimes measure the behavior of the rock using a sonic lab or seismic or what one would call a static behavior, basically like what you are seeing here. So, what are the important parameters that you want to look at? The most important parameters for elastic properties you want to look at are Young's modulus, Poisson's ratio, and Bytes constant. And we'll talk a little bit about each of those. For stresses, I want to look at the total and effective stress. So keep that in mind. I will describe each one of them in a minute. So when I look at stress, if I have a piece of rock like what I have on the left, and I'm having stress, and you can see I have a force, the force has an orientation. That can be, I can break it into its two main components, very much like what you study in math. So I can break this force in two components, one parallel and one perpendicular to the rock. So the parallel one is my shear force, and here is the perpendicular one is normal force. So if I take that normal force divided by the area, that gives me the stress. That would be my normal stress. The shear stress is again the same thing. Take the parallel force divided by the area. So if I look at a piece of rock, you look at that nice looking graph. If I have a piece of rock downhole many hundreds or thousands of feet deep, it's exposed to stresses in all directions. It's not only in one direction, it's exposed to stress in all directions. But you can break those stresses into three principal stresses. If you study electrical engineering, you remember the right hand rule and left hand rule. So they have three, you break those stresses into three perpendicular stresses and you call them three principal stresses. So they're all perpendicular to one another. Usually one is vertical and two are horizontal. In some cases, there may be some orientation to it. You know, if you're beside a mountain, you know, like near the Himalayas, near the Andes mountain, here in the United States, near mountains, these things will change. We'll talk about that in a minute. But you break the stresses into three perpendicular stresses, a vertical and two horizontal. So I will call that SV. That's my total stress. So that's vertical stress. The two horizontal stress, one usually is bigger than the other. So I'm going to call them SH max and SH min. And then your fluid will have a pressure. So there is a pore pressure inside the pores because we don't have completely solid. So there's pores inside, and this will have pore pressure. Well, it's important to think about that. And then you have also the compressive strength of the rock, which is the unconfined compressive strength is the stress that will cause the rock to fail under compression when it is completely unconfined. You call that unconfined compressive stress. And you have the tensile strength of the rock. We talked about that last week. The one thing you have to remember, like anything in nature, you move from one point to another. You want to use or you want to follow the path of least resistance. So if you are sitting at home, you want to go out, the path of least resistance to get out of the door, you go downstairs and so on and so forth. The same thing with fracture. It has to follow the path of least resistance. What is the path of least resistance for the formation for a fracture to go? You can see if I have three stresses, the fracture will have to become perpendicular to the smallest stress, because that is the path of least resistance that we have. So a hydraulic fracture will be perpendicular to the smallest principal stress, the least principal stress. So that is my path of least resistance. Don't tell me, if I ask you this question, you have to tell me it is perpendicular to the minimum stress. It's perpendicular to the minimum stress, not parallel to the highest stress. Mathematically, they are different. The answer would be when I ask what's the orientation, it is always perpendicular to the minimum principal stress. So let's look at stresses and basic theory. This is very famous graph been published by so many different people, so I just took it from, I think the first company that published it was GMI. Although when I was in Halliburton, we used something very, very similar to that. So here I'm going to look at different types of faults, and that will be an indication of the regime, the stress regime that we've got. So if I have a stress regime in what I'm looking at, the formation I'm looking at, where the vertical stress is the highest, and then you have the maximum horizontal stress, and then you have the minimum horizontal stress. If you have a fault, then the fault will go. I always like to show it with illustration, but anyway, this side of the fault will go down. It goes down because you have very high stress pushing into it. So if I fracture this formation, if I have this situation, which I'm going to call it normal stress regime. If I fracture this situation, what kind of fracture do you get? Well, the fracture has to be perpendicular to the smallest stress, and here the smallest stress is the horizontal stress, SH min. So that tells me that the fracture will be vertical and it is perpendicular to SH min. So I'm going to jump to the reverse stress regime, the last one. Here, this is not as common. Usually, the normal stress regime is the common regime. You see it in most situations for formations that are deeper than 1,500 feet or so, which is the cases that we usually fracture. They're always, and some are shallower than that, but usually it's deeper formation, and what you see is normal stress. And when I say usually, there is always exceptions to the rules. So let's go back to go down now to reverse stress regime. Well, reverse stress regime, when your vertical stress is the smallest. So your maximum horizontal stress is the highest, then followed by minimum horizontal stress, followed by the vertical stress. So if I fracture a formation like this, what do I see? Well, I'm going to see a horizontal fracture. Do you see it sometimes? Yes, it could happen. As we are going to look at what causes stresses in underground formation, I've seen it not very often, but I've seen it sometime, especially near mountains. I've seen a case like this in South America, and I unfortunately we never got the data. I wanted to get the data very badly because it was a very interesting, different situation than what you see, and it has its signature when you run testing and stuff and logging. You see a different signature of the horizontal fracture, so you don't see that very often. Now in the middle, I have a strike-slip situation. A strike-slip situation, and when the vertical stress is in the middle. So the highest stress is the HS max, the smallest stress is the SH min. The minimum horizontal stress is the smallest. So if I fracture it here, what happens? Well, what happens is we already know that that a fracture is perpendicular to minimum horizontal stress or minimum stress. So the minimum stress is a horizontal, so I have a vertical fracture perpendicular to my minimum stress. However, situation like this, you could have a problem. One is many times it becomes a T-shaped fracture. It hits boundaries between layers, and you end up having a T-shaped. So you have a horizontal part of the fracture, and that when this happens, it will cause all kind of issues during the hydraulic fracturing. Another big issue that we are not going to get into is during drilling, because now especially if you plan to eventually drill a horizontal well, as the well is deviated, you need, because as we say, is deviation, your deviation from vertical and the inclination from north or from your stresses. So you could have a lot of problem during drilling. We're not going to get into that, but this is a very important issue. So if you suspected that you have a strike-slip situation, you have to test the formation, you have to test it, because it's important to know which regime you are in. That gets you design the drilling path and the fracturing later on. Years ago, we actually, a company spent a lot of money. We worked with them in order to figure out whether it was a strike slip or normal stress. Luckily for them, eventually after we ran all the testing, it was normal stress. So let us look at a couple of cases here kind of quickly. Here I have a fault. Well, is this normal stress? Usually when I teach, I ask a student to tell me, here I cannot see you. And so I'm going to tell you, here you can see this party here went lower. You see, this is a little higher. So that is normal stress regime. This is a similar situation. You see the fault here, and you see that the little man is working on it. You can